calculus, not calculon. I don't know what that's from. A11, definite integrals, area, and the accumulation function. We're almost there, guys. So this definite integral that I talked about this on Thursday, I believe last Thursday. I put out 4 videos that talked about what the definite integral might mean and how to think about it. And in that video, we gave you this definition. It says the definite integral as an area of a region, f has to be continuous and non-negative on an closed interval AB, and then the area of the region is bounded by the graph of f, the vertical lines x equal a, and x equal b. The area is given by the definite integral here. So here is what we call our lower bounds of integration. This is our upper bounds of integration. So we have some function where a is less than b. It's non-negative on that interval, and we have some lines here, and we're finding this region, okay? Capital F, notice, because capital F is an antiderivative of lowercase f. That is, if you take the derivative of big F, you will get little x again, or little f, excuse me. Okay, so let's do an example, shall we? I appreciate your enthusiasm. So, find the area of the region bounded by f of x equal 1 plus the cube root of x, the x-axis, and the vertical lines x equals 0 and x equal 8. I drew a nice sketch there for you that tells you we're finding the area of that region. So what we do is we write the integral from 0 to 8 of 1 plus the cube root of x. I'm going to write x to the 1/3 dx. It's good to put parentheses in there so people know where your integral ends, what you're taking an integral of, that is. And remember that we had a power rule definition that said if we have x raised to the n and we want to integrate that, then remember when we take the derivative, the exponent drops by 1. So now it's going to be added by 1, and we are further going to divide by the new exponent, so that when we take the derivative, we get back to 2x. This is good as long as n does not equal -1. You can see we'll have some problems there. Okay? So, let's go to it. We have the integral of 1 is just x plus x. We're going to add 1, so we're going to get 4/3, but then we're going to divide by 4/3, so we have 3/4. So x plus 3/4 x to the 4/3 is an antiderivative of that. And our bounds of integration are 8 and 0. And so we're going to evaluate this function at 8 and then evaluate it at 0 and subtract the value evaluated at 0 from the value evaluated at 8. So we have 8 plus 3/4 times 8 raised to the 4/3 minus 0 plus 3/4 times 0 raised to the 4/3. The second one's nice, huh? This thing's getting on my nerves here. I need to save that one for later. This one, like I said, goes to 0. This one's not as bad as it looks. It's 8 plus 3/4 times the cube root of 8 raised to the 4/3. Let me do a little magic math here over the side. Notice that 8 raised, no, I took this out. So we have in here 8 raised to the 4, right? Let me not do too many steps at once. I took this 1/3 and put it as a cube root. We have 8 raised to the 4th. I want to write this as a cube root so I can take its cube root easy. So I am going to write 8 plus 3/4 times the cube root. 8 is 2 cubed. So this is 2 cubed raised to the 4th. But remember that you multiply these exponents, so I'm just going to switch them. A little incorporates our algebra that I learned at the University of Montana. And now I can take the cube root rather simply. And we have 8 plus 3/4 times 2 raised to the 4th. 2 raised to the 4th is 16. 3/4 of 16 is 12. So 8 plus 12, or 20 square units, is the area of that bad boy. Very nice, huh? Okay, let's go over to my other board here. Let's see. Don't get dizzy by this. I know that people in Newfoundland sometimes have seizures when people move tripods, but I believe that has to do with the external turbulence ambigulator. Okay, so remember this. This we knew from differentiation. We knew that if we wanted to take the derivative of a function times a constant, we could pull that constant out front and then take the derivative of the function. Similarly, if we want to do a definite integral of a function times a constant, we can pull the constant out and just find the definite integral of, or the value of the definite integral of the function and then multiply it by k. So I am doing this because the definition of area said that the function had to be non-negative on the interval. So what could this mean? And I am going to show you, using this rule then, we could write this is equal to the opposite of the integral from 0 to 2 of 3x squared dx. And that looks like this. Right? And so we know what that means. We're finding this area here. Right? But if this integral is just the opposite of this, then it is also, well, then the original integral is giving us this area here. Okay, so my point being is that if your integral is non-negative, or excuse me, if it's negative from a to b, and you take the integral of this function f of x, the integral of f of x dx from a to b, you are going to get a negative number, but it's going to be this area, the magnitude of that area multiplied by a negative number. Okay? So, what does that have to do with horses in Vancouver? Well, not a whole heck of a lot. However, we can apply it to this right here. Let's first find the integral of the sine of x, or find the value of the definite integral from 0 to pi of sine of x dx. And so from 0 to pi. And now I want to think about accumulating areas here. We're going to count the area that is positive here from 0 to pi, and let's go ahead and do that. An antiderivative of the sine of x is the opposite of the cosine of x. And we are going to evaluate it at pi, then at 0. So, opposite of the cosine of pi minus the opposite of the cosine of 0. The cosine of pi is minus 1, so the opposite of that, so we get a 1. This is a minus, so it becomes a plus, and the cosine of 0 is 1. So 1 plus 1, or 2. 2 is that area. I'm going to erase this garbage for a second. And 2. So we have from here to here, as we go along, it says the area is 2. So what do you suppose will happen when we go from 0 to 2 pi? And remember what I said, if you do the integral from 2 pi, or from pi to 2 pi of the sine of x, you're going to get the opposite of that area. And it's going to be the area, but it's going to be negative. So, what do you think will happen? Think about it accumulating. Think about it finding all these areas as we go. So it finds this positive area of 2, and then a negative area of, I don't know. Let's find out. The opposite of the cosine of x evaluated at 2 pi and evaluated at 0. So we have the opposite of the cosine 2 pi minus the opposite of cosine 0. I already just So cosine of 2 pi is 1. So minus 1. This is a plus again, and the cosine of 0 is 1. So minus 1 plus 1, or 0. Wow! Who saw that coming? I see some hands going up. That's good. Okay, so when we did this whole thing, we got 0. Let's become a little more sophisticated, shall we? And let's talk about maybe accumulating this area to some number x on the x-axis. Okay, I will write it like this. Okay, and to do this, I'm going to change my variable of integration. Instead of saying y is equal to sine of x, I'm going to say y is equal to sine of t. And what I'm going to do here is I'm going to write the integral, go up a little bit, the integral from 0 to x of the sine of t with respect to t. Okay? And now, the only thing I changed is my variable of integration. So minus cosine of t, and I'm going to evaluate it at x, and I'm going to evaluate it at 0. So minus the cosine of x minus, let me use my parentheses here, minus the cosine of 0, and we get the opposite of the cosine of x plus 1. And so that expression right here will give us the area up to any x. And we've already done it for 2 pi. But if we want the area from 0 to 3 pi, if we want to evaluate that expression, we can just put our upper bounds in here right away and say this is minus the cosine of 3 pi plus 1. Well, what's the cosine of 3 pi? This is 1 time around and then a half again. That's a minus 1. So a minus, the opposite of a minus 1 plus 1 is 2. And what is 3 pi really doing, right? It comes here and it says, okay, we're going to integrate and accumulate area all the way from 0 to 3 pi. So here we go, and we have a positive 2. By the time we get to here, we have negative, or we have 0, excuse me, and by the time we get here, we have 3. Or excuse me, 2 again. This 2 cancels with this 2, and then we have a positive 2. So there you go. You might ask yourself, you might see that if you were to integrate from 0 to 2 pi plus a half a pi, that's 4 pi over 2 plus pi over 2, which is 5 pi over 2. If we did the integral from 0 to 5 pi over 2, can you see what we're going to get here? Pi 5 pi over 2 is the same as 2.5 pi, right? So let's go. We're going along. We have positive 2. By the time we get to here, we have 0. And when we get right in the middle here, what will we have? Half of that. You're right. 1. Well, let's see if it really works. Minus the cosine of 5 pi over 2 plus 1. Cosine of 5 pi over 2, where does 5 pi over 2 live? Right there? Nope, right there. Well, 2 pi plus a half a pi. Right there. Right there, the cosine is 0, so we get 0 plus 1 or 0. Okay? So that's the accumulation function. For this assignment, you will have 4 problems that just ask you to find area on a non-negative interval, and then 4 problems that ask you to evaluate a definite integral. For the last 4, I'll tell you which ones they are. Make sure you put them on a graph of GeoGebra as your
finding the value of the definite integral, so you can see how it is accumulating area. And you can compare the amount of negative area to the positive area and kind of predict, is your definite integral going to be positive or negative? Okay? Let me know if you have any questions. We're almost done. Hang in there.